So now we get into section 480, storage batteries. Oh, here's something that's interesting. Storage batteries and battery management equipment shall be listed. This requirement shall not apply to lead acid batteries. So this is where the debate over whether or not used electric vehicle batteries can be attached to a building for normal operation kind of stems from, to say, hey, those electric vehicle batteries were not intended or listed to be for, grid tie backfeeding. And the technophiles say, well, so what? A battery's a battery, and code's kind of been stuck. They've said, we haven't required with lead acid batteries to be listed, but lithium ion batteries are even more powerful and more rapid and higher voltage, maybe higher amperage. Running a small backup load on a lead acid battery is a lot different than running a whole house. And so in the past, it's a strict interpretation of the code has said you've not been allowed to do use lithium ion on grid tie from the EV industry onto homes. And this is where it comes from. But now we've seen code come back in to say, well, right now we're going to provide guidance to say, for backup purposes and emergency power purposes, we'll start allowing you to use your electric vehicle battery to back up your whole home as well. And we've seen companies like Tesla start to make their inverters to be two directions rather than just from the grid to the car, also from the car to the grid. So overcurrent protection for prime movers. So these are starting circuits, electronic starts. It says if your electronic start is 60 volts or less, it doesn't need overcurrent protection because it's not that substantial of a circuit. Some battery definitions. The cell is the basic unit, just like solar arrays. The basic unit is that cell. We got let's see, we got a solar panel and these individual circuits on the solar panel. That's the cell. Just like a battery pack, you might have a 12-volt battery assembly, but inside that battery there's an individual section. It's the cell. The electrolyte is the liquid inside the battery that the ions move in and out of. This acid mixture is pretty interesting because it's where like your electrons, the real physical aspect of the battery that's where the magic is happening. We're going from something you can see the acid, you can see the plates, to conducting electricity in a cold manner inside the battery coming out of the cables that you can't really see. But if you work that battery hard enough, with a small battery and a very high charge or discharge rate, you can start getting ripples and bubbling in that electrolyte, and it can actually result in power quality degradation issues, where very sensitive devices might detect that agitation in that battery. Some electrolyte is not liquid, some is gel, some is solid state. And so on a gel battery or a solid state battery, you can have it be on its side laying flat instead of upright. But if it's liquid, then the battery has to face a particular direction. So we have the term for the bars that connect the batteries, called the intercell connector. And then we have the terminal, which is the last part of the battery where that external connection is made. Just one kind of finer note on the cell of the battery. A lead acid cell, It's like the atom of the battery, the least indivisible part of the battery. For lead acid, its native cell voltage is around 2 volts, whereas for lithium ion, its native cell voltage is 3.6 to 3.8 volts. And so if we're making a 48 volt battery, there's going to be a different number of cells for lithium ion versus lead acid. But you can make a 48 volt lead acid battery. You can also make a 48 volt lithium ion. And in our battery class, we kind of talk about how, even though lithium ion is really a better battery technology, a sealed battery in general cannot have the same kind of high charges that agitate that gas like an unsealed battery can. And it's common to get unsealed lead acid batteries. You don't buy, you don't have unsealed lithium ion batteries. In fact, with lithium ion, they're trying to get it into a completely solid state rather than just a gel. And all of lithium ion is going to be sealed. So with a sealed battery where you can't apply a very rapid charge, it's weird because physically lithium ion is able to take a higher charge and a more rapid charge, and we see that reflected in its natively higher voltage rating than lead acid. The problem with lithium ion is when you, just like with lead acid, you can charge it too quickly, but more importantly, with a sealed battery, you can't exceed the maximum voltage of that battery. Otherwise, the battery that's sealed, it can't contain the pressure. With an unsealed battery, that gas that's being created bubbles out the top, and you can smell it. And you're not supposed to smell it. You're supposed to be evacuating it out of the room with an exhaust fan. And so the pragmatic difference between charging a 48 volt battery bank that's lithium ion and charging a 48 volt unsealed lead acid battery bank is that the lithium ion charger setting, once you hit that maximum 48 volts, it immediately is going to throttle back the charge, whereas lead acid you could sustain at a higher voltage, which has some maintenance benefits that are simply not available to sealed batteries. Let's talk about battery disconnects. All ungrounded conductors over 60 volts need to have a disconnect on both sides. So you may have a battery bank that just has a positive or a negative disconnect for under 48 volts. Both sides need to disconnect for over 60 volts. Where a disconnect is remote controlled, and those remote controls are not within sight of the battery, like a push button on the wall that you can see, but some remote control on your cell phone that no one you can't see in the room, then the disconnecting means needs to be lockable. So they don't want a maintenance person disconnecting the battery bank and then some remote monitor being like, "Oh, that weird disconnect open. I'm just going to shut it," and with a remote control, and while someone's working on the battery bank. Says the disconnecting means shall be permitted to be incorporated into the busway, so you can kind of put it in line. The disconnect should be legibly marked with voltage and current. Ventilation. So there's two times when you need to ventilate a battery bank. The first is unsealed batteries where the ventilation is obvious. The second time is when your battery starts to get large, like in a commercial storage system, or maybe a very high end luxury home system. So it's like once you get to be like more than 100 gallons or so of electrolyte, even if it's a sealed battery, you'll need to have a ventilation system. The battery support system itself deserves a little bit of attention. So there's a couple of times when you can have a, let's say here's your battery bank, and you just want to put it on a concrete slab and just set the battery right on it. Does the structure that supports the battery should be resistant to deteriorating action? So now let's assume our battery bank is going to be twice as big, and we're going to have a shelf here, and we want to put another battery bank on top of the shelf. Well, these batteries are really heavy, so the shelf is going to be made out of metal. But batteries can release corrosive gas, and so it says the support structure should be resistant to the deteriorating action. Metal structures shall be provided with non-conductive support members. What that might mean is you have to put a rubber mat, on the shelf before you put the battery on top of it, so that the battery itself doesn't leach any electricity or voltage into that frame. And you might be painting the metal to prevent corrosion from the gas, but it says the paint alone is not considered the insulating material. National Fire Code manages battery ventilation requirements in the room. It's actually a little bit more flexible than international building code. International building code requires continuous ventilation of the battery room, whereas National Fire Code, you can have, if you have continuous ventilation, it can be a smaller amount. Otherwise, for ventilation, you need to have, there's like cubic volumes per cubic feet requirement, like a air handling air conditioner system that turns on and turns off needs to be a little bit more powerful than a continuous ventilation system. So many installs so that you don't have to have continuous ventilation in your whole room, in accordance with International Building Code, might enclose the batteries in a case and then ventilate the case continuously to the outside. So battery locations, live parts should be guarded against accidental contact. It sounds obvious. You don't want to have electrical parts being exposed where someone can just come up to them and touch them. But, you pop the hood to your car and there's your battery hanging out with its terminals exposed, surrounded by metal, and it's not, the hood protects it, but you could open the hood. Could you, if you're grabbing a wrench and you're connecting the terminals of the battery together with your wrench, could you electrocute yourself? Yeah, you can. Says live parts of an electrical equipment operating at 50 to 1,000 volts nominal shall be guarded against accidental contact by approved enclosures. Now, we say 48 volts nominal for a 48 volt battery bank, and this is saying 50 to 1,000 volts nominal, but a 48 volt battery bank is operating at 50 volts or more on a day-to-day basis. Yeah, so I would say all of your home sized battery. The intent of this is for your home sized batteries or larger to be guarded against accidental contact, whereas an individual battery for starting an engine or a motor or powering a small device is not so heavily regulated. But I was building a battery bank for an off grid house. And the customer says, "Oh, I'll take care of the battery box." I say, okay. Well, he builds a shed for the batteries. Okay. We put the batteries in the shed and wire the system up. And he comes in to the shed and he looks at the battery bank and he says, "Whoa, those batteries, if I touch the terminals, am I going to hurt myself?" And the answer is, well, yeah, you could. And that's why you need to take this shed and make sure that the door has a lock on it, because you don't want unqualified people, coming into that room. And he wasn't very happy about that because he wanted to keep like yard equipment and stuff inside the box and didn't want to keep his battery room locked. And it's like, well, that's a fundamental part of a battery enclosure area, is to have it be secure from the outside. So I've walked into a 48-volt battery bank where this project actually did not get off the ground because the installer sold him an inverter and that was too large for the battery. Would have discharged the battery way too fast. At any rate, they just had the 48-volt battery bank hanging out on a shelf in the garage. It's like, well, what is that? Well, that's where we're going to get into after the break, talking about where the code is driving for self-assembled battery banks versus pre-assembled battery banks. But we have you can locate batteries in a room that is only accessible to qualified persons, or you can put permanent and substantial partitions or screens between the battery bank and the battery area. Or traditional, keep them away 8 feet of clearance off of the floor on an elevated platform. We'll see that like a Tesla battery is now allowed to just be on the wall in the garage because it's part of a complete manufactured assembly. But the spirit of this is, your electrical parts that are live that you could touch and hurt yourself need to be guarded and protected. And that, it seems obvious, but people just want to have their batteries hang out in their utility closet in their garage, and there's more work that needs to be done to have that space be suitable for battery storage, like isolating it from the general public. Let's see. Battery clearance requirements: 1 inch between the battery and the wall. This is actually given an exemption later on for assembled batteries like the Tesla Powerwall. But if you're building your own battery bank, it needs to have 1 inch of space between the cell and the wall. There's clearance requirements between the top of the battery and the height of the next shelf that are driven by manufacturer specifications. It's weird that code says you got to abide by that, but I think they're just trying to remind you that there's, check your battery specs before you pick out your shelf height. A personnel door for battery rooms shall open outward as you're leaving the battery room. And gas piping is not permitted in battery rooms. And then finally, illumination is required. That seems a little weird, but often these battery rooms, they might be built into the side of the building. They might be reconverted into a closet, and they need to be lit up because And usually it's nice to have that lighting circuit be on a critical load panel coming off the battery inverter or something like that. So if something's going wrong with the system, if you still have a degree of functionality, that functionality is being spent to illuminate your working area so you can fix whatever's going on. And there's a section on code on capacitors, which is capacitors are super, super, super expensive, way more expensive than batteries, and that's why we use batteries instead of capacitors. But capacitors can be charged and discharged much more quickly than the traditional batteries, and we see that they're saying, well, these things are so super powerful that we're going to require you to have above the typical oversizing. So normal electric code, you're oversizing by 25% as a starting point. With capacitors, you're giving that cable 35% additional headroom rather than 25%. Acknowledging the rapid discharge capabilities of the capacitors, could be surge loads, and they want to give you a little bit more clearance. So then we get to Chapter 5, which governs special occupancies, healthcare buildings, boat docks, all of this kind of weird circumstances governed by Section 5. We're not going to get into that in class, but finally what we've made it to is Section 600 for solar. Into it. So Chapter 6 is a section for equipment that is peculiar, specialty equipment that might have their own rules. Maybe devices are on low voltage circuits, and so they might not need the same protection requirements as higher voltage circuits. Here we have a section for electric vehicle charging systems, and they're defining electric vehicle storage batteries effectively as sealed batteries. And so they have room ventilation requirements for electric vehicle charging stations. And that's pretty interesting, I think, because what that means, an electric vehicle has about 110 kilowatt hours, 100 kilowatt hours of storage capacity, and a Tesla on the low end. Higher ends might have 140 or 150 kilowatt hours. I don't really know, but it's around that range. And so once you're getting into home-sized lithium-ion batteries, just the volume of chemicals in the battery is saying you need to be able to ventilate this room, even though the batteries are sealed and not producing gas. They're concerned in a fire. If the battery bank catches on fire, and let's not talk about a situation where it burns the whole house down and kills innocent women and children and all that. We're just saying if the battery bank heats up and it catches on fire in the battery room, you're like, oh my goodness, this is horrible. It might burn for a while because the batteries, once they start going, they burn. There's a lot of power stored there to come out. And you want to be able to ventilate that air inside the room to the outside. So even though it's a sealed battery, when you get enough of these batteries in a room, you have to have ventilation in the room. Now we get to Section 690, solar. And right off the bat, we have definitions, and this one is a bit of a fumble. A functionally grounded system, which is a PV system that has an electrical reference to ground that is not solidly grounded. So if it's not solidly grounded, it's functionally grounded. All right. What does this mean? Well, on a DC circuit, you would have a positive side and a negative side, and it's quite common to tie that negative side to ground so that the negative side has a voltage potential of 0 and the positive side has a voltage potential of 12. And so they'd say, well, that's negatively grounded. Well, with solar inverters, they were taking that negative side and connecting it to ground, and that was resulting in a blind spot failure case for the inverter ground fault detection, where you had small ground faults going into ground, raising the voltage potential of that ground, and the inverter wasn't able to see it clearly. They've since fixed this inverter blind spot issue by not connecting the inverter DC negative side to ground, but having it be isolated. And when that happens, the main thing is, instead of just putting one fuse and one disconnect on the positive side and assuming that the negative side is tied into ground and is at 0, so it doesn't need the fuse or the disconnect, when you don't negatively ground the system, you put in an extra disconnect and an extra fuse, and this is called floating, where the positive side and the negative side are a 12-volt difference with reference to each other, but there's not a solidly grounded connection made to ground that brings one of these two sides down to 0. So there's no grounded kind of reference point. The DC operating circuits are physically isolated from ground. And it requires an extra disconnect switch and an extra piece of overcurrent protection, so it is a little bit more costly than a negatively grounded system. And they had to kind of figure out how to do ground fault detection for it. And so where this word mess comes from is it used to be quite common to have a negatively grounded solar inverter. Nowadays, the inverters are in a floating configuration, and people were getting confused because they're saying, oh, wait, it says it's an ungrounded inverter, but I thought it needed to be grounded. And what about the metal parts? Are they ungrounded too? Because they said, no, you can have a floating configuration inverter where neither the positive or negative side is tied directly to ground, but you're still grounding the metal parts and all of that. And so they've now called that concept as functionally grounded. Here the generating capacity of the system is defined as the inverter maximum continuous output. Some solar inverters, such as battery inverters, can surge for a minute. They can output more power than what they're rated for. Let me tell you, if you're relying on that burst capacity, don't, because a lot of heavy loads like heating loads or air conditioning loads that surge, they surge for longer than 1 minute. And these surge load capacity, extra boost capacity of the inverters, by nature are not designed to last longer than 1 minute. So the burst capacity on an inverter is less useful than you think, but you'll open up a spec sheet and it might say this is a 5 kilowatt inverter and it can boost to 7 kilowatts. Which do you use as the output capacity? Output capacity is continuous output. So maximum voltage. A solar system on a 1 or 2 family dwelling cannot have circuits above 600 volts. On other types of buildings, you can have more than that. So on a commercial business, you can have 1,000 volt system. On a residential ground mount, you can have a 1,000 volt system. Which I think that's pretty neat. You know, as a matter of principle, higher voltage and lower amperage is preferable versus the other way around. Uh, when you're going with low voltage, like our electric grid goes up to tens of thousands of volts. So the upper limit on voltage is very easy, but our conductors, you can only make a copper cable so thick. There when you're buying cable, for the most part you're buying for the amperage and not the voltage capacity, and the amperage is what gets increasingly expensive, not the voltage. The going from a 200 amp service panel to a 400 amp service panel, you're doubling the price of the service panel. When you go from a 300 volt cable to a 600 volt cable of equivalent gauge, you're just buying a little bit more plastic. You're not doubling the cable cost. So having that extra clearance of 1,000 volts can result in cost savings. Utility scale plants can go up to 1,500 volts or more. Solar cable, PV cable, is rated for 2,000 volts, which is incredible. We use it all the time on residential because it's just a nice outdoor rated cable with a thick jacket, but it's rated for very high voltage. It's kind of interesting to know. If I'm doing a ground mount that is very far away from the home, the voltage drop from point A to point B becomes significant. And the cabling cost for the amperage from point A to point B becomes significant. And the way you decrease that cost is to do exactly what the electric grid does, which is increase the voltage and drop the amperage. And so if I'm doing a residential off-grid system and the house is in the middle of the woods and the solar array is out in the field, considering building an external battery box from the house and using a 1,000 volt platform is not bad, because then you pick up higher voltages for transmitting that electricity over a longer distance. 600 volt for residential 1 or 2 family buildings. Well, that's kind of interesting. It says multifamily might be able to have 1,000 volts. 1,000 volt inverters are cheaper than 600 volt inverters. Panels are rated for 1,000 volts, solar cables rated for 1,000 volts. So putting all that extra headroom to use on commercial projects can be worthwhile. The sum of the PV module open circuit voltages of series connected modules corrected for temperature using open circuit voltage. So the way that this works is in series wiring. To determine if you get up to 600 volts, is you take however many panels are wired positive to negative, series wiring where voltage is adding up. A typical solar panel might be operating at 40 volts, but that's its operating voltage. Its open circuit voltage is maybe 50 volts. And you need to make sure that your open circuit voltage does not ever exceed 600 volts. And so we have to apply the temperature coefficient to that. And what's interesting is, even though the temperature coefficients, like how voltage is impacted by solar panels, even though that is listed on the spec sheet, and to some extent it's a manufacturer specific thing, what I always say about solar is the solar panel from company A to company B is more similar than different. The temperature coefficient factors of silicon solar panels, yes, their higher quality gives you a little bit more, but it's only a little bit. And so code will give you a voltage correction factor for solar panels that are traditional silicon to say, okay, if your open circuit voltage is 50 volts, apply this temperature correction factor to that voltage, which will increase the voltage. Remember, this voltage is done at 25 degrees Celsius. And so if you get down to, zero, below freezing, if you get down to negative 5 degrees Celsius, there's a 30-degree temperature difference. This voltage could have increased to 60 volts instead of 50 at that lower temperature. And so you need to say, well, how many 60 volt, after I'm adjusted for temperature, modules can I fit onto a 600 volt circuit? And the answer is 10. So how many panels can you fit on a circuit is calculated in code. Or you could use a manufacturer listed solution. But to some extent, that's where we get into string sizing, where you're inputting your coldest temperature on record, and it's telling you how many modules can fit on a circuit. As on that, it's checking that on the coldest day of the year, your circuits don't exceed 600 volts, or 1,000 volts for that matter. So the maximum voltage for DC to DC converter source output and output circuits, it says DC to DC converter source circuits shall be the continuous output rating of the DC to DC converter. Okay, what that means is you got a solar panel with a DC optimizer box behind it. So the solar leads are coming out of their own junction box and going into this optimizer, and then the optimizers are plugging into other optimizers that are on their own solar panels, and all of that circuit is you add up the output voltages of all these optimizers together to get your maximum voltage. And what we didn't do in that circumstance is correct for temperature. With the DC optimizers, you get a little bit more leeway because they are their own forms of voltage control. So you can use the extra length in that circuit says, oh no, you don't have to have just 10 modules on the circuit, because we can adjust the voltages and increase the amperages and keep the circuit below 600 volts during that time. And if it fails to 1 volt rather than full voltage. So it's just fine if it fails correctly. And so code allows your optimizers to have longer circuits because they are providing additional inline controls to regulate voltage and amperage to stay within that 600 volt threshold. Amperage capacity, it says, so how do we size our circuits for maximum? We say, so to calculate our maximum circuit current, we take the short circuit current. So again, there's a current is amperage, and that's amperage with an I instead of an A. Amperage is inductance. All right. So our amperage, there's a maximum power point amperage, and that's basically the operating amperage when the system is swimming along efficiently at full power. That's what its amperage is at. There's also the amperage you would get if you took all of that power and went and touched a piece of metal with a power cable and shorted yourself out to ground. How much power would be shorting to ground from the circuit of solar panels at that time? That's that short circuit current. And so for calculating the voltage, we saw that we take the short circuit voltage and then we adjust for temperature and then we add 25% headroom on that. Here, we're taking the same circuit and we're finding the short circuit current and then we're adding 25% headroom on top of that. And so far we're in the normal the normal realm of electrical oversizing to calculate the current requirement for the conductor. We're just adding 25% onto it. Or it says you could get an engineer to figure out the actual amperage and stamp it. But then we get to an additional step. And this is where how you remember all these additional exceptions is like, well, hold on, there's other things going involved. We have to do a few things. It says, well, if you don't want to do anything, just take another 25% on top of that. And so, I guess what we're talking about is that ampacity, that short circuit current plus 25%, as you would size kind of standard things in electric code, that doesn't take into account the fact that, your current, in addition to number of conductors in a cable, in a conduit, in addition to being 1 inch from the rooftop, in addition to all those things, the amperage itself will jump around as a function of temperature, and we're given what's listed at 25C. And so what code is saying is either you're taking the listed amperage for short circuit current and adding 25% to that, and then adding another 25% to that, which means, whatever the amperage is of the circuit, you're adding an additional 56% and just treating it like that's the amperage of the circuit. So you're just giving yourself tons and tons of headroom in your conductor for that electricity. Or you go through a series of temperature correction factors similar to what you do with voltage. And then it gives you an exception which says, okay, well, if you're using inline controllers, inline optimizers that are actively adjusting the voltage and amperage and have listed safety features to fail in a way that doesn't cause the system to exceed its requirements, then you don't have to have that additional 25% oversizing. So you take the output current, multiply by 25%, and that's your design current. So you take the short circuit current of the circuit, add 25%, and that's your design current. If you're using optimizers or microinverters for that matter, otherwise you're adding, if you don't know anything else about the system, you're adding an additional 25%. And so kind of when you have a solar array, like a commercial solar array, and then there's tons and tons and tons of circuits that are all being, and there's so many circuits. So, with a residential array, these home run circuits are usually just going straight back to the inverter and being managed inside the inverter itself. But on a commercial array where you just have tons and tons of solar circuits, you might use a combiner box and have a lot of circuits in and one circuit out. At least that's how old school solar used to be. And in this kind of old school configuration, all of these conductors were uncontrolled. Nowadays we have little boxes behind every solar panel, and so these conductors are controlled. But when they were uncontrolled, we were having to take our conductors and then add 25% to it, and then add another 25% to that. And so that kind of led to rule of thumb circuit sizing for solar, where the ampacity is 56% of the short circuit current rating of solar, whereas most circuits it would be 25%. But solar, you have that additional protection to account for all of the extreme temperature differentials involved with solar, which you could just go and calculate on your own too, if you wanted to, or you could use these control boxes and then you're right into just normal electrical sizing, where you take the maximum output of the device and add 25% to that, and that's your design ampacity. Uh, let's see. So we have an overcurrent device like a breaker or a fuse shall not be required for solar arrays or DC to DC converters sized in accordance uh, where one of the following applies. Where there's no external sources such as parallel connected source circuits. Right, so what does this mean? Well, we were talking about just on the other slide a whole bunch of circuits coming into a box at one point and then being tapped on to one output. The problem with this kind of configuration is that if there's a fault, like a ground fault in one of the circuits, then the other three circuits, instead of the electricity flowing where it should be going, these other three circuits can backfeed the fault. And because this cable is only rated for one circuit and not four of them, that cable, while it's ground faulting, would heat up and catch the box on fire, and that could cause additional ground faults. And and what happens when that starts faulting into the conduit, then the electricity travels down the conduit, and if there's a weak point somewhere else, that part of the conduit could catch on fire. And so to help prevent that happening is whenever you have and there's a debate on whether it's two or more or three or more, but whenever you have multiple circuits coming together, you put in a fuse rating, you fuse them so that they can't backfeed each other. The alternate to that is the solar panels themselves may have higher quality fuses built into their individual junction boxes to mitigate backfeeding. So sometimes there's some listed, so sometimes with two circuits or three circuits, you can actually get away without having the fuses if you really know your spec sheet. But as a starting point, in any electrical design, whether it be service panels or solar arrays, whenever you have multiple sources of power being tapped together, whether it's inside a box or a combiner box or a service panel or a supply side tap, you have to think to yourself, I have multiple sources of power being fed into one supply. Do I have overcurrent protection on the other side of it? And if so, if not, if there's no breaker regulating that source, then why is that the case? And it might be, well, because I'm doing a tap and it's 10 feet away from the source. So, that means if something's going wrong, I'm already right there at the source, which has its own disconnect switch, and I can just turn it off. But if you're feeding multiple distribution panels that don't have main breakers and your supply doesn't have a main fuse, and you're trying to tap onto that, just like the inside of a solar combiner box with multiple circuits. When you have multiple circuits coming together in one, you in most circumstances you need overcurrent protection on those circuits. Arc fault protection is now required on solar arrays at 80 volts or higher between two conductors, except for ground mounts. So that's kind of interesting. I'm coming around to the opinion that ground mounts are not that much more expensive than roof mounts, mainly because you can avoid the DC optimizers and the microinverters, and even old inverters that don't have arc fault detection would be eligible and still code compliant as ground mount inverters. So you can find a lot of inverters that are no longer code compliant for a home that would be suitable for the ground. Okay, rapid shutdown is a rule that has changed over time. So it says the boundary is 1 foot from the solar array in all directions, and it should comply with one of the following. It needs to be listed or field labeled. So what's the difference? Well, this rapid shutdown system is how someone at the side of the building presses a button and it turns the solar array off on the top of the roof. And that can sometimes be sold as a complete system, which then gets listed as a rapid shutdown system, or you're using disparate parts and you need to field label the method of how you're meeting rapid shutdown, because there's a couple of different ways, and it's changed like every 3 years. This 1 foot border, it used to be 10 feet, and then it was 6 feet, and now it's 1 foot. So it's changed with each code edition. What the field label needs to indicate is how what version of rapid shutdown you're on. Is it a 1 foot boundary or a 6 foot boundary, so the fire department knows how your system is rapid shutdown compliant. And then it says it's limited the controlled conductors. This is a new requirement. So rapid shutdown has gotten stricter over the years, but now they are actually regulating the conductors that are inside this 1 foot perimeter, as well as the conductors that are outside the 1 foot perimeter. They're saying outside this 1 foot perimeter, you have to kill the power when that rapid shutdown button is pressed. But inside the perimeter, you also have to lower the voltage of the system, drain it to ground over a minute or so. The problem is without, a solar array is always on, and if the sun's up, and you can isolate the solar array from the building with a disconnect switch, but you still got high voltage within that array perimeter, and that makes it very hard for a fire department to go into a building to fight the fire, especially if the solar array is what caused the fire to begin with, because then that's where the fire is, and the fire department says, well, I'm concerned about arcing electricity electrocuting the firemen while they're trying to fight this fire, so it's more pragmatic to let the building burn down. And so, this labeling is important to tell the fire department, what version of rapid shutdown you're using. There are exceptions. So at any rate, this is where the mandate for those little boxes that go behind every single solar panel comes from. That's the reason why Enphase and SolarEdge have done very well in the stock market, because these requirements have only amped up, and they were the pioneers of this market. And then there's an exception for solar shingles or frameless solar panels where you're using fiberglass racking systems that says, hey, if you don't have any parts that are exposed to conductive material, you don't need to do rapid shutdown within the array perimeter. You can still have these high voltage circuits, which I don't think is very fair because the building's burning down. I think it's safe to assume the solar array could be exposed to other things. But anyway, there aren't that many solar shingle products out there to begin with. So you have an initiation device. This initiation device cannot be more than 6 switches. It follows the 6-handle rule. It needs to start the shutdown. And it makes a note that says when you turn off a solar array that does not have dedicated circuitry for taking the isolated electricity that's still up in the solar array and draining it out of the conductors, that electricity stays in the conductors, and it can stay in those conductors for up to 5 minutes if there's no grounded circuit that is being activated to drain that voltage to ground. And so this is also kind of a problem because even if you had a disconnect switch, it still can take a while for that electricity to drain. Meanwhile, the building's on fire. So this has been a step up, trying to kind of anticipating solar fires. Now, in reality, I think that the fires that have been caused in the solar industry have not had much to do with rapid shutdown, other than rapid shutdown systems like microinverters and DC optimizers would have interrupted that fault. But it was mainly sloppy workmanship with MC4 connectors being poorly managed, lying down in puddles and burning holes in the roof and taking advantage of shortcomings in the electronics rather than the electronics themselves. And so a lot of installers view rapid shutdown as like putting Band-Aid on a problem that really wasn't a problem, but it's only gotten harsher over the years. It's not ever going to go away. So you can have the rapid shutdown initiation device be a disconnect switch, or just a readily accessible switch of any type. On some battery inverters that I've seen, they have relay inputs that you can use. We use my smart home system as a relay input into the battery inverter, where you just press a button and it turns the battery. It initiates the rapid shutdown on the inverter. So the solar disconnect should be readily accessible and marked with a warning about electric shock. And this electric shock warning is for this reason. Here we have a disconnect switch. And we have inside this disconnect switch, you got like a terminal block that the cables come and land on. You can see it has this plastic housing. It's isolated from the metal. And so inside the switch, we got a terminal block with terminals, and the grid comes in from one side and the solar array goes out the other. And you turn this disconnect switch off. What it's going to do is there's a connection point between these two circuits, and when you turn it off, it lifts that connection point upward and it kills power to the solar array, so the solar array is disconnected. The problem is you still have live connections coming in from the grid. So these terminals, even though the disconnect switch is off and this switch is open, the faceplate's up, these terminals are exposed, these terminals are still hot at the very top. And electrician, is comfortable looking at these terminals and the energized from the top, but still nonetheless opening up the lid to that disconnect switch and maybe even working on the underside of the switch away from this energized area because they know what they're doing. Someone else could misinterpret this switch being down as off and this lid being open to reach in and touch those terminals because they want to do some amateur wiring work and electrocute themselves. And that's why these readily accessible disconnect switches need to be locked so that only people who should be in them can get in them. Another lesson on these disconnect switches is you have a top group of terminals and a bottom group of terminals. And so the question is, which side does the utility land on, the top of the terminal or the bottom of the terminal? You might have an underground feed from the utility and your wires are coming up into the box from underground and the solar array up on the rooftop. You might just say, okay, we're going to put the solar array on top and the utility conductors on the bottom, and that's going to look nice and neat. The reason why that's wrong is because it needs to be consistent and standardized that when the box is open and in the off position, that the bottom of the box is de-energized and the top of the box is energized, because by nature of this lid here and height and gravity, the bottom of the box is a lot easier to work in than the top of the box. And so you don't want to encourage work on the dead side on the top of the box by leaning over the energized terminals on the bottom of the box. You want it to be the other way around. And for those reasons, the box is labeled with a line side, which indicates this is the hot side, and a load side, which indicates that this is the bottom side. And in this case, even though you have the grid, which is obviously a supply, you might also have the solar array, which might not have any load circuits on it. So you say, okay, well, which goes into the top? They're both supply. The grid's a supply, the solar array's a supply. Which one lands on the top of the disconnect switch? The answer is the supply that's always on. The grid side goes into the top. The primary side goes in the top. So this disconnect needs to be readily accessible. It needs to have a sticker that warns about the electric shock. It needs to be suitable for use. Abide by the 6-handle rule. And then it says we're going to have you simultaneously disconnect those inverter output circuits. And it's marked line and load. So that's your solar disconnect. If your combiner boxes are large, they need to have disconnects on them. They can be remote operated, similar to the battery disconnect. They need to be externally operable without exposing the operator to parts while indicating open, closed, or lockable. Some jurisdictions take this too far and they say we need to be able to view the disconnect without being exposed to operator parts. And so you need a disconnect switch with a little window in it so that you can look inside the disconnect switch and see it. That's not part of code. That knife switch disconnect where up is down and up is on and down is closed, that you can just pull up to the side of the house and look at that knife switch to see if it's open or closed. That's an indicating closed, lockable, operatable switch. It's not the only, a knife switch is not the only switch that is allowed by code to be this disconnecting means. It's just a very common one. When I'm buying a disconnect switch, it might be cheapest if you're just doing a simultaneous disconnect of each 120 volt pole. It's probably cheapest just to buy a 2-pole non-fused disconnect switch. Um, I've usually regretted buying a 2-pole switch instead of a 3-pole switch to also disconnect the neutral, because you don't have to disconnect the neutral. You can just run it straight through. But then down the road, being able to disconnect the neutral is nice for truly off-grid systems where you don't want to backfeed. The utility's concerned about you backfeeding during a power outage. Being able to disconnect fully from the grid by disconnecting the neutral as well can be useful. But it says it can be a load break fused pull-out switch, like an air conditioner disconnect can be compliant as the solar disconnect. Most local jurisdictions step in and say, no, we want you to use a knife switch. So for identification, solar circuits need to have their own raceways. They can't be combined with other loads. They need to be kept to themselves, but that can include the AC and DC conductors. When sharing a box, there doesn't even need to be a barrier. They just have to be grouped separately. So you can't have the AC conductors tie wrapped with the DC conductors. They need to be identified at all points, including splices. Which one's positive, which one's negative. Identification can be the colored cable plus numbers. Or it could be colored tape plus numbers. Now it says, if as far as single conductor cable goes, we're going to allow you to use USC2 cable, even though it's not specifically listed as solar. It says underground service entrance cable is robust enough to use as solar cable. And you can also use solar wire, PV cable, or it's really PV wire. It's a single conductor, shall be permitted as well. But it says in exposed outdoor locations and within the solar array. So, code is saying, look, this PV wire has a very thick jacket. We want you to transition into a thinner jacketed cable when you go inside the house and make it back to the inverter. Or they keep it outside. Cable tray is allowed. Multi-conductor cable assemblies are allowed. Flexible cords for tracking arrays has to be that hard service cord, not a EV cord. So here we have the requirement for metal inside the building. So still pretty early in the solar section. DC circuits, when they run inside the building, they have to be contained in metal. From the point of penetration of the surface of the building to the first readily accessible disconnecting means. All the letters on the labeling system have to be capitalized. They need to be every 10 feet. Well, this means every 10 feet on that solar circuit, on that conduit, on that metal conduit, you need to have a sticker that says, this is a solar circuit. So installers have tons and tons of conduit stickers that say, caution, photovoltaic output circuit, or solar source circuit, just to slap on the conduit every 10 feet. inside the attic, up on the rooftop, all the way back to the inverter. Access to boxes. So junction pull boxes, they can be located behind the solar panels. So what that means is here you're up on the rooftop, and here's your solar array, and here's your solar array, and here's your solar array, and you have a nice symmetric, that's a professional looking roof right there. And the question is, when you make this transition with your box, do you have to put the box outside the array and then run conduit to it and then drill into the roof and go into the roof from there? The answer is no. You are allowed to obstruct this box by putting it underneath the solar array. And it's a matter of professionalism on whether you do this or not, because a low profile box that fits underneath the solar array is a specialty item. So only solar installers really know about like the Soladeck box. Sometimes I'll get a Soladeck box that's just an empty shell and run all the way back to the inverter. If I'm using MC cable, I'll use that Soladeck box to do transitioning from MC to the PV wire up on the rooftop. But I love hiding them underneath the solar array because then you can't see it. Then it results in just a magical aesthetic where when you look up on a standard blue rooftop here, if you don't have any stuff outside of the array, you just have your solar array up on the rooftop, and everything, all the conduit and cabling and racking is hidden underneath the array in a little box. You achieve this kind of hovering effect where it just looks like the solar array is magically floating on top of the rooftop. And generally what I'll do is I'll take my box and put it at the corner of an array, so if someone's up on the rooftop they can look underneath and see where it is. Likewise, I'll get into the attic and I'll generally locate this box at the top of the array to minimize the amount of rainwater that's going to pour around that penetration. And then that's where sheltering the box with a solar panel is really the nice thing, is because you're getting that box out of the sun, you're getting it out of the rain, you're using the material on site, as opposed to having the box be outside the array perimeter with a little nub of exposed conduit. So it says the equipment ground conductor is run with your solar circuit conductors when they're leaving the vicinity of the solar array. It should be compliant. It says when it's smaller than number 6, it needs to be protected from physical damage. So this is where we talked about how installers will just run a number 6 bare ground up to the rooftop and land it on the racking and call it a day. If it's smaller than number 6, then it needs to be physically protected. That's where I'm using I usually use a number 8 that's wrapped into the MC cable. Identification of power sources. This is the listing requirements. You say, well, what stickers do I need on my solar array? Your stickers need to identify what the array actually is to an inspector or emergency responder when they show up, so they know what's going on. So the difference between if the system is off-grid or grid interactive needs to be called out. The system rapid shutdown needs to be called out. The disconnect locations, array voltages and amperages. Some additional requirements. It says the PV system output conductors shall be marked to indicate polarity when connected to energy storage systems. So positive and negative So now we're moving into Chapter 7. Chapter 7 governs emergency systems and standby systems. And what's interesting about the two is that they're different. So an emergency system would be, a hospital double redundant or triple redundant, a fire alarm system that might have its own tapped on connection to the grid ahead of a main breaker so that it doesn't lose power when the whole building does. Whereas a standby system is backup power that doesn't have these like life critical operations. So I would caution you in discussion with clients to refrain from calling, battery backup systems as good for emergencies. Use that word sparingly, because in code it has a very different meaning than what we would think of as emergency power. And standby systems are still regulated as well. And a battery inverter might not be a standby system if the battery system is not large enough or capable of providing backup power. It's just there to manage grid electric bill issues. It might not even be a standby system. Although most solar customers kind of expect that. But here's the thing: even with standby systems, it says, look, if you're going to have a load on an automatic transfer switch so that you don't lose power during a non-emergency power outage, it's a typical power outage, your source has to be capable of supplying the fully connected load. And this is the real reason why, when you look at a standard battery inverter, like the SolarEdge battery inverter, it's a 7.6 kilowatt battery inverter. But then they have a critical load side of it that's only like 5 kilowatts or maybe 2 kilowatts. It depends. But or like with the Tesla Powerwall, the power goes out, the Tesla Powerwall doesn't back up your entire house through its output. It has a critical load side that gets transferred and runs critical loads off the critical load side. And why is that? And it's because whatever loads are connected to the critical load side, code says you have to be able to power them. You can't have a critical load panel and turn it on during an emergency and it not work because it's overloaded. And so having your whole house on a backup system would require delivering enough power to supply your whole house. And that would mean you'd need a much larger and much more expensive system. And that's really frustrating to customers, because they say, well, can't during the emergency I just use a little bit of power and not as much as I would normally use. The what code is saying is automatic transfer equipment needs to be capable of supplying the fully connected load. So that does leave a little bit of gray area for interpretation in terms of, well, what if you actively manage your devices to put them into an emergency mode setting? But a rigid inspector could say, no, if your battery solar system is not rated to supply, a 200 amp service, we want you to use a critical load panel. And that is frustrating too, because you might want to back up during an emergency way more devices than what you would normally use the system to power during normal grid operation. So you might not want to manage all of your devices under a normal operation, but if you did manage them under an emergency setting, that could create a different operating condition. So we're starting to see, and we talk about this in the smart home load control class, that energy management has never been easier. It's pretty easy now to get the air conditioners and the freezers and dryers and water heaters to operate at different times. And that's opening up the new possibilities for standby power that code is not, it'll have to be updated. So the supply side connection of the system, it says all of the overcurrent devices connected to the power sources should not exceed the rating of the service. What does that mean? So I have a main service panel with a 200 amp breaker. And on the grid side of it, it's connected to that utility transformer on the side of the power pole. And these conductors are being run down for a 200 amp service, and these conductors are rated for a 200 amp service. And so if I take a solar array and I connect it into these conductors, 120 volts per leg, what's the largest solar array I can plug into these conductors? Well, the answer is the rating of the service. This is a 200 amp electric service, so we know when the utility put in these conductors, they rated them for 200 amps. And so we know that the solar array largest output that we can tap onto these conductors is 200 amps. And another reason why we can do that is all of the electricity into the service panel is being regulated by this 200 amp main breaker. So whether or not the electricity comes from the grid itself or comes from the solar array, by the time it hits the actual service panel, it's regulated by this overcurrent protection. The minute it goes above 200 amps, that breaker is going to trip. And, there's no possible way that this service panel can pull in more than 200 amps. Oh, that would be different if we have our 200 amp service panel and we're pulling 200 amps in from the grid, and then we go and we connect the solar array not to the power lines going into the house, but to the electric service panel itself. Because let's say this solar array is 40 amps and the grid is 200 amps. What that means is we could feed the panel with more than 200 amps. On a commercial project, you might have a 200 amp solar array divided between multiple inverters, and this is a 200 amp panel, and you count up the solar inverter breakers. Let's just say these are 50 amps each, and you'd say 50, 100, 150, 200. This is a 200 amp panel. Okay, I'm good to go. That's pretty easy. On a residential electric service panel, you have a 200 amp service coming in from the grid, and you go and you count all of the individual breakers on that service panel and add them all up. You're going to get more than 200 amps because code assumes not all of these breakers are going to be on at the same time. And so if you have 300 amps of breakers and you put solar on the supply side, it doesn't matter because you can only pull in 200 amps because of the size of that main breaker. If, however, you go and you put solar on the load side, you could pull more than 200 amps through this 200 amp service panel because the breakers are so many. And so in a way, the connecting to the supply side, connecting between the main service panel, and the electric grid, maybe the meter is right here and you're connecting on, the customer side of the meter, but the utility side of the main breaker. This is a supply side connection, and you can go all the way up to the rating of the service. The other kind of connection is a load side connection, where you go into, as we were saying earlier, the bottom of the bus bar here. And so for load side connections, it says, all right, you take 125% of the output circuit of your design amperage, plus the rating of the main overcurrent protection device protecting the bus bar, and that shall not exceed 100% of the ampacity of the bus bar. So what that means is if I have my main breaker, which is 200 amps, and then I have my solar breaker, and let's just call that 40 amps. And the thing is, even though it's 125% of the power output circuit, here's your solar inverter, and here's your output circuit, and you're sizing it to be 125% of this output. So it's like the ampacity of the cable, but then you're just rounding up to the nearest breaker. So there's only like an amp or 2 or 3 difference between using the breaker size or using this 125% size. So just to make things simple, we got a 200 amp breaker and we got a 40 amp breaker. And that gives us 240 amps of power. And so if this is a 200 amp service panel, it's going to heat up and burn if we supply it with more power than what it's rated for, except in one circumstance. And that circumstance is when the supply of the power source A and the supply of power source B are located as far away from each other as possible, so that their mutual power sources kind of get used up before they interact with each other. So the bottom source feeds the bottom loads, and the top source feeds the top loads, and they don't mix to combine to be more than 240 amps or whatever. If you just plug in this solar inverter wherever you want it to go, then the feed from the grid and the feed from the solar could combine together and overload the bus bar. But National Electric Code says, okay, we're going to give you a little bit of wiggle room if you interconnect at opposite ends of the bus bar. So what this means is, this is called the 120% rule. And what it means is, if you have a 200 amp service panel, you can have 200 amps coming in from the grid and 40 amps coming in from the solar array, provided that they are on opposite ends of that service panel. So it's very common on solar arrays that are 40 amps or down just to land them on the bottom of the electric service panel. Although not in all circumstances. In some cases, supply side connections are easier. In other cases, load side connections are easier. I personally think that you have to think about your disconnect switch locations, and at which point one can be better than the other. If you're doing a supply side connection, you're putting in a larger system because that lower amount doesn't work. And so if you have your electric service panel here and you're intercepting these conductors between the grid and the solar array, you might want at this point to put in a 3-pole disconnect switch so that you can fully isolate the home. You might want to put that switch right here, so that you can fully isolate the home from the grid. So if you're doing a supply side connection, I think you need to start thinking about automatic transfer switches for the whole house and start building the infrastructure for whole house backup. maybe not doing everything today, but at least putting in the appropriate disconnects and switch gears when you're already working in that area. And sometimes it's easier just to keep it simple. And for systems that are 40 amps or down, kind of just land onto the service panel until you're ready to do something more ambitious. The problem is by the time you get the solar array and the battery bank next to each other, you start to run out of space on the service panel anyway. Inevitably, if the home is going to be powered with whole house off grid, whole house battery backup, inevitably there's going to be some type of supply side interruption and interconnection. And so we see field labeling. It says, if your connection, if you're doing a load side connection using the 120% rule, you need a sticker that says, hey, don't relocate this breaker. If you're not using the 120% rule, then it doesn't matter where the breakers go and you don't need the sticker. But if you're using the 120% rule, you need to have clear instruction to say, hey, electrician, don't move this breaker because it has to be located down here. Likewise, if you're working on a load side connection, you need stickers that say, hey, be careful about adding more breakers to this service panel, particularly loads, because you don't want it to exceed the ampacity of the bus bar. Center fed panels are allowed to use the 120% rule just on one end, but not both ends. So that used to be ambiguous. That's been clarified in 2020. So equipment containing overcurrent protection devices must indicate the presence of all power sources. So an electric service panel has to say, hey, this is a solar circuit right here, regardless. We see the disconnect requirements are the same as the solar disconnect requirement. They have to plainly indicate whether it's open or shut. That doesn't have to be a knife switch, but you have to be able to look at the switch and see if it's open or shut. Lockable, simultaneous. It says the location of the overcurrent protection device has to be within 10 feet of the electrical service. What that is does this, if you have power in the meter going into the property and your solar array is really far away from it, the required disconnect is within 10 feet of the electrical service. Now, you might have to have an additional disconnect if it's typically within 50 feet or line of sight. If it's outside of line of sight, then you'll have to have another disconnect here. It's a matter of principle. But it says location of overcurrent for that device. That overcurrent could be a breaker. It could also be a fused disconnect switch. Sometimes you can save yourself a bunch of money if it's just one solar array being tapped into the grid. To not put a service panel there, but instead just you're already buying a disconnect switch. Using a fused disconnect switch counts as your overcurrent protection. Chapter 7, we got some special conditions. Interconnected power current. This is kind of like the DC optimizers. You're using the inverter output current, and then adding 25% to that, unless there are other active controls already going in line. I guess what that means is like if you have a output current and it's rated for 40 kilowatts, and you put a fuse in there that is or let's just say it's a 800 amp output system, and normally you size it to be 25% more than that, but if for whatever reason the manufacturer says put in a 900 amp fuse in line, then you could size it for 900 amps. That's a rare circumstance. uh this is saying you don't need to have that extra fuse. You could get away with a non-fuse disconnect if there aren't any parallel power circuits. If it's just the solar array going straight into the service panel and that's it, uh, as long as the short circuit current is there, it's fine. Let's see. If the inverters, we just talked about this. If the inverters are not in readily accessible locations, then they need to have disconnect switches within sight of the inverter. Basically, there needs to be a disconnect switch that a worker can look at and use, when they're working on the equipment. There also needs to be a disconnect switch where emergency responders that are just pulling up to the house right at the electrical service can press to de-energize the system. And if these locations are not both adjacent to the solar array, then you need to have disconnects in both locations. Ampacity of the neutral conductor. There's special considerations for 240 volt inverters on three-phase wiring versus 120 240 with regarding oversizing. And so on three-phase 240 volt, you may not be able to undersize the neutral. I think that's what it is. Just know there's a special exception there. Or there's another exception that says if the neutral isn't needed by the inverter to function, then you can just size it to be the equipment ground conductor size. We kind of talked about that in the early part of class. Hey, but now we're making it almost all the way through code, so just a few minutes left, and we'll get there. This is our last section, Article 706, Energy Storage Systems. Now, we already saw a section in 480, General Equipment for Batteries. This is saying battery systems that are operating at over 60 volts DC that may be standalone or interactive with other power production courses. So you could say, okay, well, operating at 50 volts AC, that's going to be most battery inverters are outputting over 50 volts AC. So we're batteries for buildings is being pulled into this scope. And you can say, well, what about 60 volts DC? My battery's under 48 volts. Maybe. I don't think it matters. I think you got to abide by energy storage systems because I think you want to be looking at battery systems that are over 60 volts. And I say this as someone who hasn't done it before. I've only done 48 volt battery banks, but I've only done lead acid battery banks. And we saw that lead acid has a lower native voltage than lithium ion, which means that at low voltages, all else being equal, I can fit more ampacity for the same number of batteries with lead acid than I can with lithium ion. But what I know about lead acid on a 48 volt nominal battery bank, by the time you're getting up to 122 kilowatt hours, which is about what you need to start really providing whole house off grid to most solar homeowners, is that you're getting up into, a volt times an amp is a watt. And so if I'm designing a system to have, let's compare 12 kilowatts and let's compare 48 kilowatts. Let's pull up our calculator and do some amperage calculations. And so let's say I'm designing a battery system for a whole home, and that whole house is a 200 amp service panel. You have to remember that that's 200 amps at 240 volts, and a volt times an amp is a watt. And so your home service panel is 48 kilowatts. If I was trying to draw 48 kilowatts of power, and that's my service panel power, but it's going through my battery inverter. And if my battery inverter is drawing off a 48 volt battery bank, that, if we're going from 48 volts to 240 volts, the voltage is increasing 6 times. A volt times an amp is a watt. And so the amperage is increasing rather substantially too. Instead of a 200 amp service, or 4 times, instead of a 200 amp service, we have 1,000 amps coming out of that battery. That's parallel runs of incredibly thick battery cable. Now, you can find lead acid battery that's rated for 1,000 amps output, but your battery cable sizes are getting into the size that you'd use for utility scale facilities. With incredibly high amperage, you're spending too much on your cable. What's more typical is a home to have maybe 12 kilowatts as a backup solar inverter, but even then you're using 250, 300 amp cable and getting up into 4-aught, which is like the thickest welder cable you've seen. And beyond 4-aught, that gets you into utility scale, cable. And so what is safer and what is more cost effective is to increase voltage and decrease amperage. And so with the Tesla battery and with other kind of battery inverters that were made specifically for lithium ion, you see in electric vehicles, for that matter, you see moving towards like a 350 volt platform. And that, taking what would be a 48 volt battery and making it into a 350 volt battery is, that 7 or 8 times increase is going to drop your amperage 7 or 8 times as well. And that means you'll get away with thinner cables in your system, which are easier to manage, less costly. Higher voltage is cheaper than higher amperage. So we're going to be moving away from the 48 volt kind of home backup power standard and into higher voltage battery banks. And this is the section that governs that. So we have different system classifications: self-contained, pre-engineered of matched components. That's not you doing the design. That's a manufacturer selling you a battery product that is really the combination of a bundle of products that are still designed to work together rather than just being made by one company. And then other, which is like, if you hired me to build you a battery bank, this is what you'd get. Someone would piece together systems, buying different batteries and different inverters from different supply chains, and that's a standard construction project. And so we got some labeling requirements, such as the clearing time of that electricity coming out of the battery conductors. So when you disconnect the battery conductors and you measure their voltage, how long does it take for them to drain to ground? We say when a storage system is more than 5 feet from its connected equipment, or if they pass through a wall or a partition, you need to have a disconnecting means at the end of the circuit. You know, and I recommend getting knife switch disconnects in this case so that no inspector says, and you need to disconnect the positive and negative at the same time. A second disconnecting means needs to be located at the equipment if the first disconnecting means is not within sight. So we need a fused supply side disconnect at the battery terminal when the two locations are more than 5 feet away from each other. So if you only want to get away with having one disconnect in line of that battery circuit, those batteries need to be within 5 feet of their end run. So that's pretty strict. The batteries have to be right next to the inverters to have simplified disconnects. So here's the one we talked about earlier where there needs to be a minimum of 1 inch clearance between the battery and the wall. Well, then you go and see nice pictures of like the Tesla Powerwall being mounted in a garage. It says, the trays can actually touch the wall in under two circumstances. You could build the shelf into the wall, but then you'd need more than 1 inch of space between the batteries and the wall. Or you can use like a Tesla Powerwall that comes pre-engineered to hang on a wall and is listed for that. And they say that's okay too. And we see requirements for egress and illumination that we've seen before. Conductor ampacity should be not less than the greater of the nameplate circuit current rating or of the energy storage overcurrent protection device. So the conductors, your battery conductors, have to be sized to be at least the size of the fuse that's protecting that battery circuit. And that should be not less than 125% of the battery circuit, kind of a standard thing. The location of the overcurrent, if you're more than 5 feet away, should be at the battery itself rather than at the equipment, so that it fails at the battery rather than at the equipment. All right, so dwelling units, not permitted over 100 volts unless the live parts are not accessible during routine maintenance. So if you get into high voltage battery banks, even within that locked storage room, you may need a partition if there's other routinely maintained equipment inside that room. This is kind of interesting. It says if you're building your own battery banks, then you need to isolate the batteries so that it break them down into 240 volt or less segments for maintenance. It says floating batteries are allowed. Okay. That's where you have a disconnect switch on both ends and fuse both ends. It's pretty common. It says flexible cable is allowed within the battery. So sometimes flexible cable is finely stranded cable, and it's frowned upon in electrical usage because of arcing, and it's less of an ability to hold up to when it's being landed on a terminal and the bolts screwing into the fine strands. They chip off. And it says, well, in a battery enclosure, you really need that extra flexibility. Flexible cables are fine in a battery enclosure, still sized to 125% of the current. There are some other sections, off-grid standalone systems or direct current systems. Chapter 8 is where you get into communication system cable.